just went through. And if you have any questions about those or any hurdles that you have, when we come back, we can address them together, and hopefully we learn from each other. All right, let's continue on with the topic that we're meant to cover. Okay, so we're meant to cover the physical layer now. All right, let's go. So I use my own PowerPoints instead of the ones that's in there. It's just the same ones, but it's cut down a little bit with more summarized information, because you can tell sometimes it's a little bit too long, too much information. Got it. All right. So if you remember last week, we talked about the 7 layers of the OSI model. Phil Donahue never televised sick people anymore. Okay, that's how I used to remember it. And if we go from bottom up, it's physical, data link, what's a network? I'm trying to think of the Phil Donahue never televised transport layer, sick people, sick session layer, presentation layer, application layer. And I can remember that in those order because of my saying Phil Donahue never televised sick people anymore. And I have to mentally do that every time I have to remember it. So there's no, it's just a memory trick, but it's up to you how you remember it, or you don't even have to remember it because there's no theory exam for this subject. Just know that there's 7 layers. And there's also the TCP/IP layers that last week we talked about. We compared them side by side. And you'll see later down in that assignment 1, you'll have questions relating to that. Okay? But let's start with the first layer, right from the bottom. Physical layer. It's probably the easiest one to understand because the physical layer, as the name suggests, is something we can touch. See this thing? That's physical. And a network cable is part of the physical layer. Okay? The access point, the radio frequencies that's emitting off it is part of the physical layer. Okay? These cable runs through the walls, part of the physical layer. These patch panels, physical layer. These network interface ports, physical layer. Okay, the device here I can touch is a physical layer, but this device actually works at the data link layer as well. So when we say this is a layer 2 device, it's because it's at the highest layer it works at. Of course, it's physical because I can touch it, but it's because it's working at the layer 2, we call it a layer 2 device. Whereas a router, we call a layer 3 device because it's working at the layer 3. And just so we don't get too sidetracked, you're probably going, why is he talking about layer 2, layer 3 devices? What does that mean? So this switch, just to give you a preview of what we're going to talk about in the future, it determines which computer is plugged in which port and where to send the frames based on the MAC addresses. That's in the data link layer. Okay? So each of your network cards, every network device that connects to a network has a MAC address, which is a physical address that's part of your network card. And that's the data link layer. And because that switch uses the MAC addresses at the data link layer, that's layer 2. That's why we call it a layer 2 device. Whereas a router routes traffic, like I demonstrated on my door, based on IP addresses, doesn't it? You send a packet to a destination IP address, you send it to the gateway looks at the destination IP address, goes through its routing rules, routing table, and determine where to send it based on the IP address. The IP addressing is in layer 3, the network layer. And that's why a router is a layer 3 device. So when I say layer 2 device, layer 3 device, that's why I'm calling it those things. But let's get back to the physical layer. Okay? The physical layer is all about the things you can touch, the cabling, the media. And that media could be radio frequencies, it could be fiber optics, it could be copper, it could be FM radio. It could be all those things, but let's keep on going. So the purpose of the physical media, it's the physical connection. Before any network communication can occur, the physical connection to a local network must be established. Literally, plugging it in. That's the physical connection that they're talking about, okay? Plugging it in, or if it's a Wi-Fi, joining the Wi-Fi network. All right. This connection could be wired, wireless, or wireless, depending on the setup of your network. And this generally applies whether you're considering a corporate office, the home, so it's everywhere. A network interface card, or NIC, is the device that we connect to a network with, whether that be a wireless NIC, Ethernet NIC, fiber optic NIC, they're all network interface cards. Some devices might just have one network card, or NIC. Some devices have multiple NICs. So if we look at this device, there's only one Ethernet network card. Okay, that plugs into the physical network through an Ethernet cable. That's fine. But if we look at this computer here, it's got this physical Ethernet, which has this blue cable plugged into it. So it's also got this little antenna. All right, this little antenna here. So it's actually got multiple network interface cards. So if we actually go back and look at okay, it's got even more than that. It's got Bluetooth, it's got Wi-Fi, it's got Ethernet. Just ignore these two for now because they're VMware virtual adapters, but these are the free physical adapters. So you can have more than one NIC on a device. Not all physical connections offer the same level of performance. We all understand that. We know that the Wi-Fi could be a little bit slower than the Ethernet. We know that Bluetooth is certainly slower than the Ethernet. All right, so physical layer transports bits. So don't forget, at the end of the day, computers deal with bits. There's ones and zeros, binary. And next lesson, we'll actually talk about binary more. But it accepts a complete frame from the data link layer and encodes it in a series of signals transmitted in the local media. So let's not worry too much about the data link layer and the frames, but basically, if you want to think about it, we use an application. We put a message, and so if we think about the 7 layers, the user is the 8th layer, if you like to think about it. The user uses the application and goes through each one of those layers before it's sent through the physical media to the network. So each one of those layers is passing on something to the layer below it. So in this case, the data link layer is going to send an Ethernet frame to the physical layer. The physical layer then takes the media, whether that be electrical signals, electrical impulses, light impulses, radio frequency, and then encodes it into the media. Okay? So this is the last step of encapsulation, and encapsulation is basically wrapping it up in layers. So the next device in the path to the destination receives the bits and re-encapsulates the frame and decides what to do with it. So let's not worry too much about the higher layers. We're focusing on the physical layer only. So these are some standards, okay? You probably heard of the term ISO standards. Maybe not so much these other ones. Maybe the last one. Has anyone heard of the IEEE? Maybe. If you studied engineering, you would. Okay, special electronic engineering. So it stands for International Electrical Electronic Engineering. Basically, no, never heard of it. That's okay. I've got cousins who are electrical engineers, so that's where I hear it from. But you'll get used to it. Okay, so the physical layer standards are implemented in hardware, are governed by these organizations. So what do I need to do I need to know all of that? Probably not really. What I need to know is the fact that it's a standard. Standard means it's the same way of doing things across the board. It doesn't matter if you're using a Realtek, Intel, or Netgear, they're all going to do things the same way. Okay? So if they don't do things the same way, they're not going to work with each other. So that's what these organizations ensure. So the physical layer standards address 3 functional area. the physical component. So obviously, it wouldn't make sense if Intel makes a connection that's 2 centimeters wide, and Netgear makes a connection that's 1 centimeter wide. It just doesn't work, does it? That's the physical dimensions. The encoding, how it sends it, the ones and zeros, how it encodes the ones and zeros, it has to be the same. Otherwise, if I send it through an Intel card and they're receiving it through a Netgear card, they wouldn't be able to understand each other. And same with the signaling with the lights or the electronic radio frequencies. Physical components are hardware devices, media, and other connectors that transmit the signal and represents the bits. The hardware components like network interface cards, interfaces, and connectors, cable material, cable design are all specified in various standards. So encoding. Remember we said that it's all ones and zeros, but how does that work with electricity? So if this is the voltage, if this line is 0 volts, sorry, this line is a medium. If there's a voltage, it could be counted as 1. If there's 0 volts, it could be counted as 0. You get me? So if I said that if I'm going to talk in binary now, and I will make a sound when it's a 1, and I'll leave a gap of no sound when it's 0, then you probably could detect that, couldn't you, with your ears? With the electronics, that's the same, okay? But the problem is, there's no such thing as 0. You know how you see this really sharp lines like this? You're either 1 or you're 0. There's no such thing. It's more like a wave, in the sense that it's never going to be exactly 0. So you've got to have some thresholds where this is anything above this level is going to be detected at 1, anything below this level is going to be detected as 0. And that's what these standards would tell you. So this is this is actually what it looks like. Okay. So signaling method is how the bits values, ones and zeros, are represented on a physical medium. The method of signaling will vary based on the type of medium. So this is actually what a electrical signal actually looks like in reality. Remember, I said there's no such thing as these nice sharp lines, because in the real world there's no such thing. There's interference coming from all over the place, and you've got something like this. But if your software is good, you probably could recognize that this is a 1, 0, 1, or could be 2 ones actually, but depending on how it takes it. But it takes something like this and basically turns it into like that. Do we need to worry about it? Not really. We're not the ones designing these things. We're the ones that are plugging it in and using it. So however they do it, it's done. That's why we don't need to be concerned about it. It's not our job. Okay? As long as they're obeying a standard, then it's going to work. Just so you know, so this is the digital signal for voltage, okay, ones and zeros, and you can see there's a period. So within this time, that's where it's going to be detected as 1 binary digit. Okay, so this period could be a millisecond. It doesn't matter. It doesn't matter to us anyway. So you can see that this is maintaining the ones, but because it's gone through 2 periods, it's detected as 2 ones. But again, it doesn't matter to us. Just so you know, this is AM. You've probably heard of the term AM radio. AM stands for amplitude modulation. So it's the height of the waves or the power of the signal changes, and that's how they encode a 1 or 0. Okay. So you can look at this. You can see that these are lower peaks, if you like, than this one. So these lower peaks might be detected as a 0. These higher peaks might be detected as 1. So that's how AM works. How do they get all the signals to transfer across the air through that? They just change the height of the waves. Okay. What about FM? You heard of AM radio. You heard of what's that? You probably heard of FM radio. FM stands for frequency modulation. Frequency is how many waves you can fit in a set period of time. You can see you got these wide waves and you got these narrow waves. So these these wide waves might be seen as a 0, but these narrow waves, which you can get lots of waves in one time, is seen as a 1. Okay. Then what about this one, PM? You probably heard of that in terms of time, but not in not in the terms of signaling. But what it stands for is period modulation. So if you remember in your high school, you talk about waves. So if you go from one wave to another wave, full wave, that's a period. But you can see that, whoa, this is just weird. It's like it's a weird joining here, isn't it? Because they've actually shifted the period. They've shifted the wave. So you can see that this should be it should be going up. But instead of doing that, they've shifted the wave as if it's gone past another part of the wave. So again, do we need to know exact workings? Probably not. If you want to do the Cisco exam, probably yes. But for us working knowledge in IT and networking, no. We know that Wi-Fi uses radio frequencies. Doesn't matter which one it uses. No. Does it work? Yes. If it doesn't work, then that's where we're investigating. All right. What about bandwidth? Bandwidth is a measure of speed. Okay. I'm sure you all are familiar with this because one of the first things you learn about when it comes to your phone speed, your internet speed, or your transfer speed, or your hard drives, you're looking at bits per second. 1 bit per second, BPS. Okay, that's like one or 0 per second. That's a very slow. Kilobits per second. Okay, that's probably dial-up speed back in the day. If you remember, if you were around back in when we had the telephone cables with dial-up, 54K per second, and 54 kilobits per second. Megabits per second. This is probably talking about our normal internet connections now, NBN or ADSL. ADSL was 1.5 to probably 25 at max. But now NBN, we've got our, probably typical home is about 20, 25 megabits per second. Business can be a lot higher. Then we got gigabit. This is probably our LAN speed, like we talked about before. Your typical LAN speed or speed of your local area network is gigabits. What about terabits per second? Oh, that's getting a lot bigger, and it keeps on going, doesn't it? So these terminologies, each one is like 1,000 of the previous. It's not exactly 1,000, okay? So it's not exactly 1,000. We'll talk more about that next lesson, but it's not exactly actually, it is exactly 1,000. Yeah, if it was megabytes and kilobytes, it's a different story. So what's latency? Latency is lag. If it's like when I say something and the time you hear it, if it takes you like 5 seconds, that's a 5-second latency or lag. Okay? It's just like when you see an airplane, but you don't hear the sound until a little bit later. That's the lag, that's the latency. Okay? Because basically with the airplane, the light gets to you a lot faster than the sound gets to you. And the difference is the latency. Okay? Throughput. Throughput is a measure of the transfer of bits across a media in a given period. How much data can you get through a medium? Okay? Good put. That's really not really a good term, but it's a good put. A good put is a measure of usable data transferred over a given period. Good put is throughput minus the traffic overheads. Just if you think about it, how much groceries can I get in my Coles delivery van? Oh, it might be 2 tons of groceries, but how much is the whole van including groceries? The van itself might be 1 ton, and your groceries are 2 tons, so your total throughput on the road is 3 tons, isn't it? But the actual amount of groceries you get is 2 tons, because 1 ton was wasted on transporting the truck itself. Okay, so that's if you're talking about petrol, we're wasting petrol on transporting truck, but we can't get the groceries without the truck being transported as well, right? So what good put is basically is just the groceries. Okay, and and the cost of transporting that truck or transporting the groceries is the overheads. Copper cabling. Copper, that's a metal, isn't it? So if you know that most electrical wires are made from copper because it's a good conductor, it's the most common type. It's the most easiest to install. It has the lowest resistance to electrical current flow. Okay, so it's very good in a lot of ways. But there's some limitations as well. Attenuation. What does that mean? So if I was talking to you and I went further and further away from you, the sound of my voice is going to be less and less as the further I go away, right? Basically, that's what attenuation is, where the strength of the signal decreases over distance. Okay, just like my voice would decrease. You guys at the front probably getting full volume, but the guys at the back probably getting less than that. But same with copper, with electricity. As you go through the copper wire, the resistance of the copper is going to reduce the amount of electricity at the end of it. Okay, so after a certain distance, you can't really hear it anymore. After a certain distance, you can't hear my voice anymore. After a certain distance, you cannot detect the electrical signal anymore. Okay, attenuation, the longer the electrical signal has to travel, the weaker they get. Electrical signals are also susceptible to electromagnetic interference. Okay, heard of that term? EMI, electromagnetic interference. Basically, the way they generate electricity is to pass a magnet over copper wire. That's how you generate electricity. So if you have a magnet nearby, and you can actually change that electric current. Okay, so if you have these nice ones and zeros, you put a magnet right next to it, those ones and zeros might be distorted to the fact that you can't recognize those ones and zeros in those nicely anymore. So what does that mean? That means that if I have to send my, let's go back to the scenario of the assignment. We've got a factory floor. We've got, first of all, if we use copper through the factory area, if you don't know what a factory area is, lots of machinery, heavy machinery, lots of electric motors. Electric motors has magnets in there. If your cable goes too close to these machinery, it's going to change, it's going to affect the electrical signals in the cables, and by the time it reaches the PC, you might not be able to recognize it anymore. Okay, so that's the problem. So it's susceptible to EM interference and radio frequency interference and crosstalk. Crosstalk is where even the cables, as you pass electricity through these cables, there's actually an electromagnetic field around the cables, and that electromagnetic field could interfere with the current of another cable. So you see how we've got these channels. If you look back here, we've got channels here, but under your desk. Okay, that's probably the easiest way to look. So you can see there's electricity power, and electricity, as well as cable for data, right? You see that very quickly? Okay, you can see that for us here, you can see that the electricity is on the bottom channel, and the cables, the blue cables, are in the top channel, and they're in a metal box, if you like, metal conduit. Can you guys see it? No, it's not open. So if you have a chance, have a look over here. It's a bit open over here, but they're separated by different channels. Okay, so basically they've got cable up here, and they've got the electricity going through here, and all these things are metal. Okay, so that metal sets up a sort of shielding. Okay, so what about all these problems? Okay, how can we mitigate? Mitigate means make those problems less. Okay, we have strict adherence to cable length. So with copper, you'll realize there's a 100-meter cable length maximum. So anything more than 100 meters, you have to put another device in between. Okay, so a repeater, a switch, whatever, but each piece of cable can't be more than 100 meters. What about some kinds of copper cable mitigate EMI and RFI because they have shielding. So those are just typical Ethernet cables, but you can have what's called shielded twisted pair, where instead of just having a plastic cover here, within this plastic cover there's actually a metal foil that protects against the interference coming from outside. Okay. There's also, the crosstalk. If you haven't looked at one of these cables, if I remember, I just talked about this last time. You can see there's a whole heap of little things in here, different colors. They're all different cables. Remember we talked about crosstalk? Each one could interfere with each other, right? But in reality, those cables are twisted against each other in a certain rate so that crosstalk is minimized. Let's have a look at this. So these are the little cables that's inside here. You see how it's been twisted? All that twisting is actually minimizing the crosstalk. This is what's called UTP or unshielded. You can see it's just plastic, and then you got the cable. This is shielded twisted pair. You see that foil? That protects against electromagnetic interference from the outside world. This is a coaxial cable, a bit like your antenna at home, if anyone still has an antenna. This is what we used to use, and you used to have a copper core and outside, and it gave you heaps of problems. So you can see there's the twisting, and this is the most common type of media, and it terminates in an RJ45 connector. So RJ45 is just those connectors. Yeah. Okay, they look like the phone connectors, but fatter. They're called RJ45. Okay, so the shielded twisted pair has this foil. Okay, so that foil. Have you heard of the term the Faraday's cage? Okay, if you don't remember that from your high school physics, basically if you have a cage around something, the electricity will go around that thing through the cage rather than go inside of it. So you could be standing in a room and lightning could be striking you, but if you have that cage around you, you'll be safe because the lightning will go around that cage into the ground. But this is effectively what it's trying to do with this foil. This is the coaxial cable. We don't want to spend too much time on this, but this is an old-fashioned type of cable. No one uses this anymore. The only time you see it is probably in your antenna. But we used to use this in the networking. But it used to be so terrible because you have to terminate it, and if one computer was unplugged and you don't terminate it properly, the whole network will be down. Okay, because it actually, seriously, it just went around the room, and each computer had to plug into the same circuit. Okay, unlike us, where each computer is connected back through what individual cable back to the telecommunication closet. So what about UTP? Okay, properties. It's unshielded twisted pair. Why is it called twisted pair? These are 4 pairs, aren't they? There's brown, white, green, white. They come in pairs, and each pair is twisted against each other, around each other. Okay, so there's no shielding. Cancellation. Each wire in the pairs of wire uses the opposite polarity. One wire is negative, the other one is positive, and they twist together, and the magnetic field effectively cancels each other out. Basically, that's the rate of the twist. It's not just any rate. That distance between the twists is actually done specifically. So we have okay. I thought there was a big question. Variation in twist per foot in each wire. Each wire is twisted at a different amount, which helps prevent crosstalk amongst the wires. So what it's saying is that these wires, each one is twisted slightly different, and again, they cancel the thing. Again, do we need to know the rate of twist? No. Do we need to know why it's twisted? Yes, but we don't need to know exactly how the rate of the twisting. Okay, just the fact that it's twisted and why. Okay, the standards. What's it? The TIA, EIA. Remember, that's one of the standards. 568 defines the cable type. You got the categories, Cat 5, Cat 6, Cat whatever. You can see there's many other ones, but the different categories determines the speed and the standard it has to obey. And basically, that's as much we need to know. These are the RJ45 connectors. They go on the end of the cables. We can make our own cables if we wanted to, but sometimes you can have a poorly made one. You can see there's a big gap here. So this thing here crimps down or clamps down on the jacket. And if it's like this, it's actually not providing any mechanical strength. And that can be pulled out very easily. Whereas this, you can see part of the jacket is underneath. So that mechanical strength of the jacket is there. These ones, one side plugs into your PC, another side plugs into the wall. The wall looks like this. It runs through the cables along the wall, up into the roof, down to the back of a patch panel, and they get patched into here. And on the other end, they look like these. And then they get patched into a switch, usually. All right, so there's the different layouts, and this is a T58 2568A layout. So the color coding. So that's, if you take any two cables, you'll notice that the colors are exactly the same order. You can see this is a B formation. If you look at that, the order is different, isn't it? If you have two sides which has the same order, it's what's called a straight through cable. Okay, that means that it's for normal networking. Okay, a straight through cable plugs your computer into a switch. But what if you don't have a switch? Okay, if you don't have a switch, in the old days they used to use what's called a crossover cable. So they're actually, the cables are sort of crossed over in the middle, so that you can have one end which has got this color code, another end it's got that color code. So when we go from one computer directly to another computer, they can talk to each other. Why is it doing that? Have you guys as kids played that telephone game? Like when you have a string and you got a cup on each side and you talk into it and your friend puts on their ear. So if I'm talking, they put it on their ear, you can hear them, right? But the problem is when you plug it into a computer, each one of these pins is either for listening or talking. If it's a straight through, it's like as if you both got the cup on your ear. You can't hear each other, can you? Or you've both got it in your mouth. So what the crossover does means that it crosses so that the cable that's on the talking goes on the other side for the listening. That's what the purpose of the crossover. We probably don't care about crossovers so much these days because of the fact that we've got switches as those devices. But at home, if you want to have a two computer network, you could use a crossover cable. All right, so fiber optics. So this is where we're talking about glass fibers. This is not common. It's very specialized, and you actually need a proper license to do any of this cabling. And if you don't get it right, it just doesn't work. If you don't terminate it properly, if you don't polish it to a certain level, the signals will be unusable. But the benefits of fiber optic is that, it's not as common as UTB, but it's very expensive. It's more ideal in some networking scenarios. It can transmit data over longer distances at higher bandwidth. Just think about light. Light goes pretty fast, doesn't it? Longer distances, because it's actually it's using light. Again, the attenuation is less. So for something like if you've got a long distance, let's go back to our scenario. You got the office, you got the factory floor. How far away is it? Is it more than 100 meters? Because the copper cable was limited to 100 meters, if you remember. But this fiber optics cable can go kilometers. Okay. It's less susceptible to attenuation because it really is immune from the electromagnetic or radio frequency interference. It's made of flexible, extremely thin strands of pure glass, uses lasers or LEDs to encode the light. And the fiber optic cable acts as a waveguide and transmit the light between the two ends. So the middle is glass, and they basically shine a laser or LED through it. A single mode fiber has only one light, one beam of light. Okay? But multi-mode fiber, you can shine multiple beams of light, but because they're bouncy at different angles, you can basically send two channels of communication or multiple channels of communication down the same fiber optic. You can obviously see from that this is going to carry less data than the multi-mode. So yeah, so this one, very small core, uses expensive lasers, long distance. This one uses a larger core. It uses less expensive LEDs and transmits different angles up to 10 gigabits per second, so it's faster, over 550 meters. So this is more, the single modes for more longer distances. Okay, so we've got the fiber optic cabling. So you might have heard of where they use enterprise networks for use for backbone cabling. Remember we said the backbone, the key highways between your different networks. The fiber to the home, so in your NBN, fiber to the home, the fiber is the fiber optics. If it's going to your home, it means that it's getting that high speed to your home. Long haul networks, so long distance ones, used by a service provider to connect countries and cities. Submarine cables, remember I said that, if you remember last week, we talked about how there was a typhoon or something in one of those Pacific islands, and they lost all their internet connection because these submarine cables, these undersea cables, were damaged. So that's how do we connect the whole world next to each other? We've got these cables running from continent to continent. These are some fiber optic cables, connectors, and you notice that they're always in twos because one's for sending and one's for receiving. Your ears and your mouth. One for talking, one for listening. If you only talk or you only listen, you can't have communication. Okay, so it doesn't matter which one, but there's a couple of different ones here. These are the patch cables. So instead of using those copper ones for patching individual devices, we can use these fiber patch cables. So here we go. So if we talk about UPT, we can go from 10 megabits to 10 gigabits per second. Fiber optics can go from 10 megabits to 100 gigabits per second. The distance for the copper is 100 meters max. For this fiber optics, it's up to like 100 kilometers. Is it immunity? There's no immunity, very low, lowest media connector cost, low installation skills. You don't need much skills. Safety precautions, not much safety precautions. But the immunity is high from these EM fields. It's a high immunity from electrical hazards. The cost is the highest. The skills to install it is high, and safety precautions. In all honesty, if you shine those lasers into your eye, you can actually damage your eye. So never actually look into those patch cables that we talked about before. If you want to see which side is the transmitting, which side is receiving, shine it to your hand. You'll see a dot out of the one that is actually transmitting. Oops. Okay, what about wireless? Okay, wireless. Wireless, it carries electric signals by representing the bits and binary digits using a radio or microwave frequencies. This provides the greatest mobility. So we all know wireless. We can walk around and still have coverage. We're so used to it now. Some of the limitations is the coverage area. So I'm sure you probably notice that at home there might be an area that you don't get Wi-Fi, or it's very slow. There's interference as well. There's so many sources of interference. My Wi-Fi network could be interfering with your Wi-Fi network because they're working on the same frequency, same band. What about security? Well, if I don't have to be physically in your house or in your business to connect to your network, then I can connect to your network from anywhere. So it's harder to keep secure. What about a shared medium? So it's using Wi-Fi. Wi-Fi is just using the air. If I've got a Wi-Fi device, you've got a Wi-Fi device, we're sharing the same air, aren't we? So therefore, it's called a shared medium. So what does that mean? It means it's half duplex. It can either send or receive. Whereas with the copper and the fiber, we can send and receive at the same time. That's called full duplex. So if you want to think about it, if I'm full duplex, I can communicate twice as fast as someone who's half duplex. So there's all these standards. The IEEE again, there's the 802.11 standard for Wi-Fi. For Bluetooth, it's 802.15, etc., etc. And these are WiMAX and Zigbee are less common. Well, for wireless LAN, instead of a switch, we have access point. Instead of a network Ethernet network interface card, we have wireless interface cards. There are a number of WLAN standards. When you're purchasing a Wi-Fi adapter or access point, you have to be aware of these standards. Okay, at home, I'm guessing you probably have N, and someone mentioned the 2.4 and 5 gigahertz. So if you've got N, you probably could be using both of those ranges. If you've got A, B, you're probably just using the 2.4. But the latest standard is actually AX, and it's called Wi-Fi 6. In your assignment, you'll have to look into that. But the problem is, what if one device is capable of Wi-Fi 6 and another device is not? Then they can't actually use that standard. They have to drop down to a lower standard, assuming it's backward compatible. Okay?